we'll continue with the multidimensional spaces. Okay, so once again, this is the introduction into this idea, and what we're doing here is trying to understand high-dimensional spaces through lower-dimensional spaces. That is the prime idea. So you can imagine. Well, you can imagine that. I guess to appreciate the difficulty of the task is imagine yourself two-dimensional. Can you imagine yourself two-dimensional? So this is you. Okay, and there is nothing else. So you cannot see the third dimension. This is, you see it this way. So if this is you, and maybe this is me, but the point is that the third dimensional vision, even if vision is not available, it's not only you have to move like this through the plane that you can see. There is nothing else. You cannot not only move in that direction. It might not even exist. You don't know. So all you know is your two-dimensional world. Okay, now you're trying to understand the three-dimensional world. Exactly what we're trying to accomplish, except we are three-dimensional. We're trying to understand four dimensions. Okay, so the how. Well, little by little, and it is pretty much mostly almost entirely about mathematics. So we're going to proceed in one dimension at a time, moving from dimension 1 to dimension 2, from 2 to 3, from 3 to 4, and the transition from one to the next is what teaches us new things. That's what this person would do, actually. If I was two-dimensional, what would I do to understand three dimensions? Here it is. I would think of myself as one-dimensional, okay? And then I would understand what's the difference between one dimension and two is, and then apply that idea to understand the third dimension. Okay, so we are lucky we have more dimensions available, so we can start with dimension 2, but still it's pretty much the same plan. So specifically you do it only one idea at a time, and we are starting with the distance. So we pretty much already have figured out what the formula is supposed to look like. Well, that's actually a three-dimensional formula, so that's even nothing new here. But we can imagine what would formula in dimension 4 look like, and we already know that probably will have one more term, but why? Okay, so when it is not a space that is or a location tangible, we cannot actually measure anything there to confirm that this idea makes sense. So the idea is to see more three-dimensional in the four-dimensional space. So remember, once again, two-dimensional space is a stack of lines. Three-dimensional space is a stack of planes. So we always have something we're already familiar with in order to understand that high-dimensional space. Okay, so that's they don't have to be stacked necessarily, but the whole space is made of planes pretty much. So let me try to carry out this plan with distances and how we progress from lower to higher dimensional spaces. So this is what I mean. So starting from scratch, so I will start with x1 axis. Okay, I will be counting the dimensions. And I put the origin over here, okay, and I'll just do, and then I put here point, say, A1. So what has happened is I move from 0 to A1 units in the x1 direction. Okay, and then how far? From 0, the question is, we haven't answered it. It is, let me call this point P1. So point P1. Okay, so how far? So the distance from O to P1. This is notation you may have seen. Vertical lines, even though there are various notations that are equally acceptable, but this one is the most typical. And it is equal to literally A1. Absolute value. Okay, in case we have moved in the opposite direction. So absolute value of our coordinate on the x-axis. Okay, so that's step number one. So we are living in a one-dimensional space, and we know we can measure distances. Okay, so then we are moving to the next level. What might happen is, so we realize that there is a second dimension. So this is all there was, and then we realize there is a second dimension. So maybe like this. So this is x2. Okay, so what do so that there is another axis that we suddenly realized seeing, and it is perpendicular to our axis x1. So once again, it was one-dimensional space. Then we realized it's two-dimensional space. To understand that two-dimensional space, we drew an axis x2 on that plane, and so we have now xy plane, and not just plane, but we have xy plane, the Cartesian two-dimensional system. And then also what happens next? We move from P1 to P2. A 2 units in the x2 direction. Okay, so once again, it's P2, like this. Okay, so this is my point P2. This is the coordinate A2 on the x-axis. Okay, so same question stands. How far from 0? How far from 0? The formula from last time, the Pythagorean Theorem gives me OP2 is equal to square root of, what is it, A1 squared plus A2 squared, right? Okay, so the question is, planning ahead, there's a better question to ask than how far are we from 0, but rather what is the square? So what's the square of the distance? Why? Because we're going to reuse this information. So, and then OP2 squared is equal to A1 squared plus A2 squared, where P2 is once again, P2 has coordinates A1, A2. Okay, so P1 had one coordinate A1, and now we have a P2 has two coordinates, and we know the square of its distance to the origin. Okay, so first of all, let me draw it. Let me draw that what we have found. This is what we have found. Okay, so that distance is now known, like this. Okay, now we still sort of growing dimensionally. So we were two-dimensional entities, and now we realize that we're actually living in a three-dimensional space. Okay, so it is literally three-dimensional space, and we are suddenly have an extra dimension in going from our plane into a perpendicular direction, and that's the very first step to explore the next dimension, is to add an extra axis. So we add an axis of perpendicular direction to our plane. Okay, so it doesn't have to be, if you think about it, it's the space. All the axes that we have are entirely our creation. Remember, we make up. It's like Euclidean line, Euclidean plane, Euclidean space. We study them with those axes. Okay, so I add the axes, one more axis. Okay, so that more axis will go in the perpendicular direction. So that will be x3 axis. Okay, so now we understand more or less now how this operates. We once again can find coordinates of points. I'm not going to go over that again. Yes?
Would A2 be squared there? Your orange circle.
I'm sorry, I missed that square what you're thinking. Okay. So with 3 dimensions, what we acquire right away is the ability to represent points in the space as triple of numbers. We talked about that already. Okay. So now, what about distances? This is how we proceed. We say we move from P2 to P3. Okay. How A3 units in the x3 direction. So that P3 is now has 3 coordinates, A1, A2, A3, and let me demonstrate that motion. We will be moving in the vertical direction like this. Okay, this is going to be our new point right here, and this is point P3, and the coordinate is here. So see, this little coordinate over there is the coordinate, the third coordinate of our location. Okay, so the question is the same. The question is the same. What is the distance OP3? Okay, so we did that last time, but there is a slightly easier way to think about it, and that is, and then make a point that we suppose we are still two-dimensional entities, and this is entirely in our minds. So we cannot really travel through three-dimensional space. So we feel better if we understand the whole thing with nothing but two-dimensional ideas. So what I'm going to do is I'm going to take this out and just take this picture and just simplify it slightly. And this, by simplification, I mean removing stuff that might not be as important. P1, P2, as far as distance is concerned, then our coordinates are really not important. So this is not important. What are you doing? Not important anymore. Well, actually, I don't need this axis anymore. I don't need this axis, or that axis for that matter. Right? We only care about the distances, and one of the distances we already know. That distance is from O to P2. That's from the previous step. And we also know how far from that point P2 we went to the point P3. So that we also know. Okay, so the picture is complete. As far as the finding the distance is concerned, we don't need anything else. Okay, I don't know what happened. Okay, so this is my O. X's have been removed. This is the complete picture. We know the distance of the base, and we know the what we see at the top. So in fact, I could do it this way, just to make a picture slightly simpler, like this. This is my. It is a rectangle, right? So this is the point O, the origin. We move to P2, and then we move to P3, right here. And this is once again A3. This is X, 3 x's. The X2, X1, X2 x's have disappeared because we just don't care. As far as this is concerned, we don't care about that. Okay. So and then to find the distance we're looking for, OP3. It is a diagonal, right? OP3, look, it is the diagonal direction, this one. Well, let me maybe use a different color, green. Okay. This is OP3, okay? So, Pythagorean Theorem, as always, so OP3 squared is equal to OP2 squared, right? One side, this is the right triangle, plus A3 squared. I don't need absolute values, okay? And then what do I do? I substitute, right? So substitute this in order to simplify things, and it does simplify. So OP3 squared is equal to A1 squared plus A2 squared plus A3 squared. Okay? So that's roughly how it works out, and it could be entirely understood by a two-dimensional being, because as long as you understand that mathematical part of adding the third coordinate on an axis that is perpendicular to our axis that we already had, being perpendicular, that's the important part, being perpendicular to the two axes x1, x2, the third axis is perpendicular to everything else which is within every other line within the plane, the horizontal plane, x1, x2 plane. So not only that my axis x3 is perpendicular to x1 axis, to x2 axis, it's also perpendicular to that edge that we actually care about, the orange one. Okay, so that's why it works out so well that we have a right triangle again. Okay, so and then that's almost like the whole thing is left here. But you can imagine that in the same manner we can continue on and now move on to dimension 4, right? So we know already that what's going to happen is we're adding an extra, it's 4-dimensional space, whatever it is. We add the fourth axis perpendicular to the first 3. Okay, so hard to visualize, and so we're not gonna. But we know that there is full perpendicularity of everything, so which means that my fourth axis will point somehow in the direction perpendicular. That's x4. We're adding x4. It will be perpendicular to whatever we have on our picture. It will be perpendicular to both x3. As you can see, it's also perpendicular to OP. OP2 as well, OP3. Okay, so it's perpendicular to everything. But so far, it's once again, the picture becomes still 3-dimensional. So we're adding the 4th dimension, but as far as distance is concerned, we're only facing 3 at a time. Okay, so once again, we have that rectangle they are facing, the diagonal of which we know the picture is picture is unfortunate. Let me slightly fix it. So I want to make it clear that maybe like this. Okay, so that's my x4 axis. And then we continue on in the same fashion. So the way I describe it is step number 4. Move what is it? A4 units in the x4 direction to a point P4, which has now 4 coordinates. A1, A2, A3, A4. This is how far we go, so this is A4, okay? So once again, but the picture we are facing is 3-dimensional. So as far as we certainly can handle distances, pretty much staying within dimension 3 only. And so my point will be, so if we, no, I didn't quite do it right. What I meant here is that we're moving from P2, we're moving to point P4, this many units in the x2 direction. So this is my new point, is here somewhere. So this is my P4. Okay, so but the picture is, like I said, in 3-dimensional. So this is okay. Okay, so what do we do? What do we do next? Well, you remember what we're trying to find. So what is OP4? The distance, that is. Well, how do you know? Right. How do you know? Do you see it? So we'll add an extra term to that sum right above. So let me write the answer. Okay, OP4 squared is equal to OP3 squared plus what? A4 squared. Okay. So you already know where it comes from. It's the same source. The source is what? What? Yeah, and the Pythagorean theorem, right? So we are quoting the Pythagorean theorem again, and we're using the previous distance because we already know this distance. Let me mark it here. This is the distance that we know, which is this, okay? But now a new distance that we are after is this one. From O, the origin, to the new point P4. We're quoting the Pythagorean theorem on the grounds. The only ground that we could is that this is a right triangle. Or in other words, that what I have here, let me try to outline better this is, what is the shape that I am outlining? What? This one, these 1, 2, 3 in black. It's a rectangle, right? So this is a rectangle, and we're looking at its diagonal, right? So a rectangle is diagonal, it is a right triangle. Okay, so why is it rectangle? Once again, because our axis, x4 is perpendicular to both x3 and OP2. Okay, so and that we're moving in that direction. So and then we OP4 squared is a1 squared. We substitute a1 squared plus a2 squared plus a3 squared plus a4 squared. Okay, so that's how you handle fourth dimension. We did it. We first learned how a two-dimensional person would handle 3 dimensions, and then now we are 3-dimensional entities. We handle the 4th dimension, and then it continues on in the same fashion. So you can imagine step 5, step n. Step n will be the same. We will have, what we're going to face is the picture will be almost indistinguishable. Well, in fact, let me take that picture that we have over here, which actually this picture is not. I want you to notice that. Look at this one. I want you to see that so you almost have see 3 pictures. Compare the first and the last. You see what they have in common?
Yeah, rectangles.
They are rectangles. You can see 3 axes. Well, one of them is not necessarily an axis. That OP2 is not an axis, but it is a straight line. And all of those 3 straight lines are perpendicular. The whole picture is entirely 3-dimensional. Both of them, the first and the last, both of them are 3-dimensional. We have rectangles, and we are after the diagonal of that rectangle, we found it. So as you can see, we already started repeating ourselves. Okay. So just to take this whole thing all the way home, let me take this picture and sort of make it n-dimensional. I mean, it's not going to be n-dimensional. That's the big point here is that the picture will be still 3-dimensional, but I will just change the markings. Okay, so imagine that. 3 will I'll replace 3 with n. Okay, so. This is xn. So at the previous level, we reached nth dimension. Okay. The point that we're looking at was point Pn. So imagine that we're looking only at that with coordinates a, n. So this is a1, an. So a string of n numbers. Okay, that's our location. But that's the location is in n-dimensional space, where the picture itself is still 3-dimensional. So the picture is still 3-dimensional. Okay. This one is Pn minus 1. That is what we have faced before. Okay. So Pn minus 1. That was the previous step. We moved from Pn minus 1 to Pn. Okay. And then we make one more step, and this is the point that is closest to us. The point is Pn plus 1. A little bit off, like this. The rectangle doesn't look entirely like a rectangle, so I'll have to work on that a little bit, like this. Okay, and then we're creating the axis, xn plus 1, right? That's let me erase it. Xn plus 1 axis that's been added. This one. The point, once again, is n plus 1 over here. No, not the point, but rather coordinate. N plus 1. Okay, so the picture is exactly the same, only the marking has changed. And we're dragging these 3-dimensional pictures through our dimensions, higher and higher dimensions, but we're still being able to handle that with nothing but a 3-dimensional illustration, which is, well, being on a piece of paper, it certainly has some challenge to it, but it's all at least it's all here. Okay, that is my plane within a 3-dimensional space, and the diagonal the distance from O from Z. What's wrong with this thing? OP n plus 1 squared by the Pythagorean theorem. Once again, I'm doing the same thing. This is step n. And I am moving, and so it is equal to that right triangle. I could plot it, let's plot it just in case. So that that rectangle is here, okay, with that point in the diagonal is Pn plus 1. This is An plus 1, okay, and what else? Hold on a second. This is the origin, okay, and this one is Pn minus 1. Hold on a second. Yeah, Pn, okay, okay, and then this is the diagonal we have, okay. What we're about to find from the right triangle, we conclude once again. So it's OPN squared plus AN plus 1 squared, and altogether we end up with that whole sum, A1 squared plus all the way through AN plus 1 squared. Okay, so that gives me the n-dimensional distance. Under the assumption, of course, that that space that we are creating is built in our image, in the image of our three-dimensional space. So we're building the n-dimensional space from our three-dimensional space. If that's the case, then this distance, which is still called the Euclidean distance, still works, or should work. So let me write out that formula. So so this one was a somewhat simplified situation when the one of the points was the origin, but in general it's still applicable. So no, doing it again. Nope. Final. Okay, so let me write up our conclusion. I want to just write up our conclusion, so it would be for us later to be used. Okay, so the distance, that is the definition. So once again, that's the difference between a three-dimensional space. We are checking everything with measure. So we're saying there is an idea of distances that we bring from the real space, and then we match it with the Cartesian distance or distance formula that we have used. Here it is different because there is nothing real about it. So it's all abstract. So we actually introduce the distance in a manner that is just makes sense. So we make sure that it makes sense. If the world is made of Euclidean pieces, then this distance makes sense. But we still cannot claim that that's what it is. We can only say that. We can only ask this to be accepted as the distance. How do we measure distance in n-dimensional space? That's how. That's one way. So the distance between 2 points. So P is equal to A1, AN. So this is in our N. And Q, which is B1, Bn. Okay, so points are represented as strings. Not represented as strings. They are strings. There's really nothing else. Is defined to be PQ. Once again, this is the notation we're going to be using from P to Q. Absolute value symbol. That's pretty much what it is. And then what the formula we already know, it will be B1 minus A1 squared plus B2 minus A2 squared plus Bn minus An squared, square root. Okay? it's always a good idea just to make sure that everything works out as planned. And so you plug in n equal to 1, 2, 3, and you really realize that we have recovered the formulas for respectively 1, 2, and 3-dimensional Euclidean spaces, including the absolute value. So if n is equal to 1, there is only one term, right? And n equal to 1, then PQ is equal to square root of B1 minus A1 squared, which is the absolute value of B1 minus A1. Okay, so this is the one-dimensional space. Okay. Okay, so the a couple of things that suggest to us why this makes sense, in addition to the way we build it, the way we sort of discovered it, that formula for the n-dimensional space that was made up anyway. But there are some properties that are very nice and helpful, and they just demonstrate that everything is as expected. So, for example, to begin with, that the distance is positive, unless, the only single exception is when P is equal to Q, then PQ is equal to 0. Okay, so the distance works as the distance. Even though the space is n-dimensional, it is abstract, but the distance, the way that we have constructed, works as expected. So distance between any two distinct points is positive. The distance between points that is the same is 0. Okay, so that is to be expected, and we have it. Not just to be expected, but rather to be required, and it is satisfied. This is called the positivity property. The second property is symmetry. From P to Q, the distance is the same as from Q to P. Okay. The third one is called the triangle inequality. Are you familiar with the triangle inequality from Euclidean geometry? I mean, I'm sure you are familiar with it. Just I wonder if you know what it means, or can recollect it. That's right. That is the triangle inequality. So I'll say A, B, C, and the idea is A plus B is then larger than C. That's the triangle inequality, and that comes from Euclidean geometry. Okay. And then A, B, and C we would refer to them as lengths of the sides of the triangle, and this time we are talking more about distances, but it still works out. And why does it work out in the first place? It's actually Q and R, let's say, because once again, everything in this n-dimensional space, well, not everything, but a lot of things are just hidden two-dimensional or three-dimensional things. So look at this triangle. Even though you can imagine, and let's try, so that these points, P, Q, and R, are located in the n-dimensional space. But what about the triangle? Well, the triangle is also located in three-dimensional space, but how many dimensions do you need for a triangle? 2, right? So you can imagine that this is actually in the plane. Even though the points, everything is in dimensional space, but to handle this particular triangle, one triangle, all you need is a plane. So there is a plane there somewhere. Just like, same as Euclid said. He said, well, 2 points determine a line if they're distinct points. And then he also said that 3 points, unless they are on the same line, determine a plane. Okay, so same applies to not only to three-dimensional space, which is what Euclid had in mind, it applies to n-dimensional spaces as well. So then the whole situation is three-dimensional, so it's no surprise that we end up with a triangle inequality. We just have to put it appropriately, such as PQ plus QR is larger than or equal to PR. Okay? There is one exception, obviously. It is not an exception, but rather when is it equal to when these two things are equal to each other rather than larger, it is when everything lies on the same straight line. So it's a degenerate situation, degenerate triangle when the third vertex lies, say, on the line P, Q, and R like this. So in that case, we have an equation rather than inequality. Okay, so we have built the n-dimensional space with distance, which means that we can measure things. We can do a lot, but just a couple of caveats. Especially dangerous in the case of n-dimensional spaces, and which means that whatever way you need them, they will be abstract and they will be made up by you or whoever creates a model, and then it is very easy to think to assume that that's the only way to do it. One problem is suppose you, as I have mentioned, one of the places where you see n-dimensional spaces is say a space of prices. The space of prices, say commodities. Okay, so you have 100 commodities and you have 100 prices, so you have 100 dimensional space. Okay, so far so good. There is nothing wrong with up to this point. But then what you ask yourself, what is the point of this? Well, the point will be, so suppose you have two combinations of prices, P and Q, or maybe there is a third one, R, maybe. So the point is that you ask yourself which pairs of combinations is P closer to Q, or is it closer to R? How do you know? In the n-dimensional spaces, once again, this is R100. Okay, so it is strings of numbers, and you're observing a particular situation, a particular combination of prices, and you want to, and then you've seen other combinations of prices previously, and then you want to compare this current situation to previous situation, and maybe you will compare it to today to yesterday and the day before yesterday. Okay, so you have to actually know how close they are. How do you do it? How do you find it? That's what we have been talking about, right? So you just take PQ and PR, and you can compare them together. These two are computed by our formula, no trouble whatsoever. And so you compare which one is closer, which one is farther, and so based on that you may draw some conclusions, right? The problem is that your model might have trouble if you just do it in a mindless fashion. And the thing is that we assumed, as we are we brought our understanding of the three-dimensional space to n dimensions. And what is so special about our dimensions, our space, is it's all uniform, homogeneous, and in a number of ways. In particular, it doesn't really matter which way we're going to put the x-axis. It doesn't matter. They are all equally valid. However, here in that situation of prices, so these are prices. Each dimension is a price of a particular commodity. And then one commodity is measured, I don't know, if it is wheat, and it is measured in bushels. And something else is measured oil in barrels. Okay? So even though the units are the same, dollars, maybe. But if you change oil from barrels to, I don't know, tons, the whole thing changes. The whole space is remeasured, and then your Euclidean distance also will change. And then these relations might also fail. They might not be, you think they're closer, this close to that, according to your Euclidean distance, and then it might be meaningless. Why? Because it's really, whatever you're discovering should be independent of units, right? So whether you measure, money in dollars or euros, or you measure weight in kilograms or pounds, should produce the same results in your analysis. But if you do it this way, it might not be the case. So that's the caveat. And there are ways out of it. Let's just say that there is a way to tweak our formula in order to, in a number of ways you can tweak the formula and end up with in a place that is pretty as good as this. And the idea is just to rather than take the sum, you can just add, there are some coefficients that have some meaning depending on the axis, and you will have the same. The formula will be different, but it will be just as good. So it will satisfy those three properties. It's like well, I don't know if you are familiar with space-time metric, which is actually, I mean, anybody interested in physics? Space-time? Well, you think space-time has 4 dimensions, and then you just do Euclidean distance, right? But it's not entirely correct, because spatial dimensions is combined with a temporal dimension, and they have different units. So you have to be very careful if you apply a 4-dimensional formula, this 4-dimensional formula to space-time, and they don't. So they're very careful. That coefficient, there is an extra coefficient there that would make what? Make units to match. Because once again, imagine you have 4 dimensions. Let me take that example. So 4 dimensions, x1, whatever was x1 minus a1 minus b1 minus b2, a1, machine, again, there is 2 distances existing separately, spatial and the temporal, and they simply should not be casually combined together in one formula. Okay, so you have once again b1 minus a1 squared plus b2 minus a2 squared plus b3 minus a3 squared. So these are the my spatial coordinates of 2 points, and that's the distance between them. But then I might add, say, t minus s squared. Okay, so you see a problem here. Once again, if you want to add the 4th dimension as the time, as it's casually done. However, that distance formula won't apply for a simple reason that the first 3 terms, the units might be, say, feet, and the last one is seconds or minutes. Okay, so you already they're already on a shaky ground. So that would have to be taken care of. So don't overestimate the importance of the universality of this formula. So Euclidean space, even though it is the same thing as far as the algebra is concerned in those points represented by coordinates, that remains, but the distance can be measured in a number of ways. Okay, depending on the nature of your situation. One actual example that I like to bring up, which is more tangible than physics or prices, is the so-called taxicab metric. Have you heard of the taxicab metric? In a large city, you live in a grid. So to get from this point to this point, what's the distance? This? That's not the distance. The real distance is this. Okay? So you measure distances like this rather than diagonal. So diagonal is the Euclidean distance, that is what we have. But if you really want, you know, people who live in large cities, then they know they measure distances in blocks. That's exactly what it is. So, and that's the taxi will take you. You know, it's, even on foot, you probably won't go diagonally. But if you take a taxi, they will definitely will measure how many blocks you're going to take, and that is no joke. It's really the way to measure distances. And so that's another caveat about the Euclidean distance in general and its applicability. Okay, so all right. So vectors now. Okay, let me. Okay, so we almost have 5 minutes left. Okay, so let me just say a few words, and we'll just wrap it up. So from coordinates, now we know how to measure distances. One thing that we're going to worry about is angles. That's the second idea, that second problem that we have to be able to solve with our geometry. and distances and angles, and the angles are usually measured not between lines or triangles, but between vectors. Okay, so that's what we're after. So then we have to define vectors first in order to approach this issue. And we already saw vectors appearing once when we do that algebra. Remember solving equations. So the xy. So once again, a say 1, 2, 3, 4 matrix multiplied by xy is equal to say 1, 0. Okay. So solving a system of equations. This is a vector, a Euclidean vector, and that's also a Euclidean vector. And then we have a function from vectors to vectors. Okay, we just need to understand what is so special about vectors, beginning without any coordinates. So the coordinates are helpful, but they do not pre-exist neither points nor vectors. So we have to understand vectors just in this manner. So imagine that you have a piece of paper and you have vectors drawn on it with no help for the Cartesian system. So anyway, we'll just resume this next time. Okay? See you next week.